what I want to start out is trying to, I claim that in a one-parameter family between Morse functions, the only sort of non-Morse things that can happen are births or deaths of critical points, which is given by this local model. I want to talk about now, like, suppose you see a particular, if you're given a particular Morse function and you see some critical points on it, how can you decide if it might be possible, if it is possible to create such a homotopy that eliminates two critical points? And so, the main claim is that if you're given f and Morse function, one, let's just make it simple, we zero in on the level where there's only two critical points, let's just say, only two critical points, P and Q, or I could just say, they're right next to, they're adjacent, they don't have any critical values between them, so you can then narrow it down to just a level set, a slice that contains just those two critical points. It's like f of P less than f of Q, and index of P, Q, the index of P plus 1. And if you find a gradient-like vector field V, such that I'm going to say things slightly differently from how I said it before, such that so this is a gradient-like vector field, such that there is exactly one flow line from Q to V, Q to P. So I've been talking about intersections of ascending and descending manifolds inside intermediate levels. But if you think about it, if you have a single point where the ascending manifold and the descending manifold intersect inside an intermediate level, then you take that point, you flow up, you flow down, you get a flow line going, connecting one critical point to the other. So points of intersection in level sets correspond to flow lines, right? Going from one to the other. And if you have only one flow line, that means in the intermediate level set you have only one point of intersection. Okay? Then there exists a one-parameter family, S of T, canceling. I want to at least sketch this. Let me first emphasize why exactly one is important. What about two, for example? Two flow lines. Well, here's a simple dumb example to point out that take a circle and you have an index 0, if this is P and this is Q, and you have two flow lines, and you obviously cannot eliminate, right? That's sort of a dumb example. But there is also, there's another thing to think about, which is that if you only think about the vector fields, then at least in one higher dimension, if you find an isolated flow line from one critical point to another, if you only care about the vector fields and not about the function, you can sort of cancel them. So here's the thing. So just looking at vector fields, this is just some sort of general ideas to develop your intuition. So you could have, let's say, a point. What you're going to see typically is that, let's say this is the point Q, and this is the point P, and you're going to see a single flow line from Q to P. Maybe Q is, say, a saddle. So then your flow trajectory is going to do something like this. Q, and then P would then have to be a sink minimum. And it's worth thinking about, if you just look at the vector field, there's sort of a general picture that's worth absorbing as to how the cancellation works. You want to say the cancellation sort of happens just in the neighborhood of this single isolated flow line. And so it's a little hard. I claim that you can modify this vector field so as to eliminate these two singularities of the vector field. This would go to stare at it. We have stuff coming in, stuff coming in here, stuff coming this way, coming out here. Tilt. I mean, if you just look at this, sure, it looks like stuff is veering to the right here, but in the end, you just sort of have stuff going in here, and out there. So of course, you can sort of connect up these flow lines in some way. So that you don't have any singularities. So from a dynamics point of view, just thinking about the vector field, it's worth pointing out that you can cancel even if there's. But so what happens if there happened to be another flow line from Q to P? Maybe there was another flow line that went around the side. Suppose this went over and came back in here. What's going to happen there is that you're going to get something that comes back around here, and you're going to get a closed loop in your flow. And of course, something special about flows for creating like vector fields or Morse functions is they should have no closed loops, right? Because if they had a closed loop, well, they're supposed to be always going down. Gradient. This is my down vector field. Sorry. I can't get away from thinking of downward flow. So this is my minus V, I guess. Anyway, so if they're always going down or always going up, you can't have closed loops. So there's no closed loops for Morse functions. So that's sort of another example of why you really need just one curve point. That's just the background. So, sketch proof claim. So, I mentioned this before, you're going to, you want to, the idea is to slice the picture along the flow line in the following sense. So you reduce to, I've got my point, Q is my higher point, there's Q. Here's my point Q. I have the single flow line down P. I'm going to draw a two-dimensional picture, right? So this is my single flow line. And I just have that single flow line, and then I want, so this is, the first point is that in this flow line leaves Q in a certain direction, okay? So that's a one-dimensional subspace of the tangent space at Q. And of course, that's a direction. There's the other direction out. That's the same one-dimensional subspace, and I can flow down in that direction as well. And I know I don't hit P. Okay, so that flow line goes down, and also at P, it comes in some direction, which is a one-dimensional subspace of Q, and I can So of course, if this direction, this is the point about it being a non-degenerate, an actual Morse critical point, is if this direction goes down, then this direction also has to go down. Now, the ascending, this is part of the descending manifold, so it's all directions, right? So similarly, this is going to be part of the ascending manifold for P. So if I go out the other direction, I go up and I can go all the way up past Q. So this is there's going to be a part of it locally that looks like this, right? What am I really drawing here? I'm going to work in a, I'm saying I want to reduce to this picture. This is a two-dimensional picture. And of course, in this two-dimensional picture, you can cancel. I don't, this is just, I won't go through anything formal to say that if your picture looks like this, then you can reparameterize domain and range, so it looks like a cubic, okay? And once it looks like a cubic, then you can, cubic with two critical points, and you can add some linear function to eliminate the two critical points, okay? So what do I mean a little more precisely by reducing to this picture? So, I want to draw one higher dimensional version of that picture and say what I mean. Let's see if that helps. So we could, so let's reduce to. Okay, so let's consider one higher dimensional picture where I have local part of the my little piece of my cobordism that looks like this. Here's my top of this little slice. Let's see. Careful here. So this is, well, suppose this is what you were given, right? This is Q and this is P. Again, here's my unique single flow line. Here's my full descending manifold, and here's my full ascending manifold for P. Okay? And I want to work only in a neighborhood of the descending manifold for Q union the ascending manifold for P, and I only want to modify the Morse function there, okay? So the whole modification is actually going to happen inside, so that's my unique, color domain anything. So this is my unique flow line. And I want to, I want to the important thing is I want to emphasize I'm not going to modify just things in the neighborhood of the flow line. I'm going to modify things in the neighborhood of the corresponding to this flow line. I'm going to extend that flow line out the other direction from Q and out the other direction from P, and extend this flow line all the way up to here, and extend this flow line all the way over there, and I'm going to get some so extend so I want to find a one-dimensional part of the descending manifold for Q union the ascending manifold for P that contains the unique flow line. And this part is going to be, so it's one dimensional, so I'm just gonna, it's an interval. Interval. And it's getting an interval on which, let's say x is between, well, it's an interval and on which, just restricted to that interval, f looks like this function. Okay? So in other words, So does everyone understand what I mean? So you pick, you've got this tangent vector to this unique flow line here, and you take minus it, and you continue along. You just continue along the flow that way until you go below P. That's the important thing, right? So we go all the way down to, this is a fixed coordinate, we're just working inside here. And then similarly, you extend out this direction, and you go up along the flow all the way. So this is really a union of three flow lines. It's a union of three flow lines, and of course the points P and Q, and to be very precise, P and Q, because they're not in the flow lines. Okay? Everyone understand the three flow lines I'm talking about? There's the given flow line, there's the one that starts in the opposite direction, right? And so it's, if you like, every flow line actually has a unique limiting, any flow line that limits on Q as you go up has a unique limiting tangent vector, a well-defined limiting tangent vector. And we take the one that comes out this way and do the same thing. Question mark?
So there's some way to sort of symmetrize the. So I mean, I guess if you have Q if Q looks like your
right.
model for.
That's right.
Like
Then locally the descending manifold looks like just simply the x1 up to xk plane.
So you know that.
And so this is coming in some direction in the x1 up to xk plane, and so we just take the opposite direction the other way.
Okay. And then P.
Similarly, this is going to be the x. Oh, that was whatever index this is, whatever index this is. You've got the xk plus 1 up to the complementary plane here, right?
But there's not necessarily coordinates that put. There's not necessarily a single chart around.
There's not necessarily a single chart around both of them. That's a good point, right? So maybe I should. So I will say this a little bit. So around P, right? We have around P we have some charts, and around Q we have a chart, right? Let's give a name to this unique flow line. Let's call it L. Okay, that's our unique flow line. So around P we have x1 up to, let's see, P is actually index, P is index k. Maybe I should do a little better. That's how this P. That's how this P, so from left to right. So this is x up, and it's index k plus 1, and then x k plus 2, up to xn. And then here's the point Q. And around P, we have, let's say, different coordinates, y1 up to yk, and yk plus 1 to yn. And what we know is that L, remember, the important point was that our gradient-like vector fields are standard with respect to some coordinate system, some Morse standardizing coordinate system in here. So we picked this so that the gradient vector field is standard with respect to that system. So then we know that L comes in along the x1. So L is in this plane. And so we can extend it out in a unique way. Similarly, L is in this plane here. So you can extend it out in a unique way.
Okay. And it sort of does whatever.
And it does whatever, yeah, it goes. Okay. And now I claim that so this is a one manifold now. This large, let's call this we call this all that whole thing L prime. Okay, so L prime now is this one-dimensional thing. Okay, and now I claim that in the two-bit neighborhood of L prime, so let's use coordinate xk plus 1. I'm thinking of it as coming from Q on L. Okay, and we can actually, like up to shifting, but up to translating by something, we can this is coming in the k plus 1 direction, we can make it come in here in the k plus 1 direction. So xk plus 1 and yk plus 1 are, well, if we allow ourselves to make this not be 0, right, xk plus 1 is equal to yk plus 1, maybe plus some constant. Okay, so we can call them, we can assume that these are the same coordinate, xk plus 1 and yk plus 1, right? And now I want to what I want to do is take all the other coordinates here on which the function looks standard and translate those coordinates along this using the vector field, the flow line, right? And also translate them out this way and translate them out this way. So I claim that then can get coordinates, can find transverse coordinates x1 up to, maybe I should have called them the z's or something, they're sort of going to come from. But if I can get them by propagating the coordinates from here either way. So x1 up to xk and xk plus 2 up to xn. So these are just, actually I'm just going to use these extra coordinates here. So right here, f is going to be standard. It's going to be it's going to look like the standard Morse function here, and then so it's going to be minus sum of squares here, and then it's going to be a minus squared in that direction, and then a plus sum of squares in the other direction. So such that I want f near p. Well, basically I want to say such. What I want to conclude is such that f on this neighborhood is the sum of the minus x, the sum for I equals 1 up to k minus xi squared plus this, some, I'm going to just say plus f restricted to L plus the sum for I equals k plus 2 up to n of xi squared. So it's going to be just whatever is happening along this line L, which looks like this cubic, which I can make standard, and then, so I think, I said this was a sketch of a proof. I don't want to, the idea basically is that you've got this upward direction here, and you can flow that upward you've got upward coordinates here on which it's increasing, right? And you can flow those down and they'll stay up, right? They'll stay pointing up, and they get here and you can get them to line up with the upward directions here and then continue up, right? And so in some small neighborhood around here, everything just, this picture there's only ups, right? But you could just as well have some ups and some downs here, right? And then you flow all those ups and downs, and you can make them line up with the ups and downs here, and then keep going up, right? And so that's going to standardize this whole thing in a neighborhood of this thing. And then once you got that, then all you have to do is, so you make this part look like x k plus 1 cubed. Well, it's at some fixed time, it's going to be minus, we want it to be the one that does have the two critical points, so minus xk plus 1. That's the one that does have a pair of critical points, that's the one. Anything that looks like this can be parameterized to have this exact form, and then we know that this can be canceled with. So you're going to modify everything just in the small neighborhood, and you're just going to, you're only going to change the fk plus 1 coordinate, and that'll be canceled with xk plus 1 cubed minus t xk plus 1. So then when t becomes, plus t here or something. So when t is negative, you're here, and when t is positive, they've gone away. Okay? I think that's all I want to say. These things are obviously painful to write down in excruciating detail, but that's the point. But I think it's really important to understand that you need to go, if you just, here's the point, if you just see this for f, right? So if you're tempted to say it's going to happen in a neighborhood of L, and that's wrong, because if you just see critical point and critical, let's go back to the first point is you're boiling everything down to a one-dimensional problem, okay? And then in the other n-1 directions, you just have something standard happening. If you just see this function, you cannot cancel these critical points because there's no way to get to that, right? You want it to be pointing up here and pointing up here and no critical point. You really can only cancel them once you go down the other side and go below this critical point. Go on this side and you go up that, above that critical point. And then you can cancel there, right? And so, for example, if you want, well, I'm sort of done with that argument, and I want to sort of now generalize things.
Is it not enough to go above one or below the other? Does it have to be both?
Oh, okay, so what if you see, right, you're right. What if you go
Yeah.
that? That's actually good enough,
Okay.
right? Because then you can modify that to, I didn't draw it big enough to really make it clear what I'm talking about. This is all you really need, right? You need some level in between, right? And then you can just, you're right. However, so this is a little overkill, but it's slightly more convenient to talk about it that way. So just as a simple example, this is going to segue into the problem of pushing critical points up and down past each other, which is the next thing we'll talk about. Something you'd like to say is, suppose you just see you've got a bazillion critical points, and way up here is an index 3 critical point, way down here is an index 2 critical point, and you look at all the flow lines and discover a single flow line from here to here. You'd like to say that you can cancel those critical points. And, well, the problem is there may be all kinds of other critical points in the middle that get in the way and cause problems, right? And so, as a simple, again, one-dimensional example, you could have, if you want to, something like this, right? And suppose, of course, I mean, you could be clever and first cancel these two, and then cancel these two, and then cancel these two. But you don't have to be so clever, right? Suppose you want to first cancel these two, right? What do you have to do? You have to first arrange that you first have to push this critical point up. Okay, so step one would be you have to first modify the Morse function near this critical point to move it up. Now you've got this entire piece of the conversion here. Actually, if we wanted to really apply, actually, let's be even more careful. We want to apply exactly what we just proved. So we want to get everything out of the way. Even though this isn't really in the way, just to apply the theorem, we want an interval in which there are no other critical points. So let's be really safe and push this guy all the way down too. Push that down. And once you've done that, then you can do the modification that in this thing, and you get this is what used to be orange, was this segment here, and now you can cancel it. So the point is, in order to cancel, you may need to push things up and down. So, in general, you need to move critical values up and down. There's sort of another way to see why that might be why that's sort of obviously true, because if there is going to be a one-parameter family that makes these two critical points cancel, they're going to get closer and closer together. If there's other critical values in between them, they, eventually get right next to each other, of course they have to, cross these values, right? I mean, so we can draw a little surf graphic for what happens with this thing that says 1, 2, 3, 4 critical values. Critical values, there's this one, then there's this one, then there's that one, then there's that one. And what I'm doing here is I'm first pushing this up and this down, the values, and then these are coming together like this, and then these are coming together after that. Everyone understand how this picture relates to what I did there? Okay, this is the graph of the critical values over time.
So if from another perspective, you could, instead of moving the others out of the way.
I could have canceled those first.
But instead of pushing them away.
I could have left them, right.
You're bringing the other two closer together.
You're right, exactly. I could have just, so I could have.
It's the same picture.
Right, it's the same picture, exactly, but I could have just done, sorry. These guys, and these guys just stay where they are. Or I could, of course, have been cleverer and just cancel the first two first, and the second two after that. So now we want to talk, let's write down a similar sort of lemma about when you can move critical values up and down, and this is sort of easy. So the claim is that given, again, we're just going to focus on the case, right? Just two critical points. So just two critical points. Q, I'm not even worried about their index. Two critical points P and Q, they're the only two critical points. So I've zeroed in on a piece of my coordinates in which there's just two of them, and I want, let's say, f of P is less than f of Q, and I would like to drop Q below P, right? Then, or raise, well, just I'll say drop it, right? So, and the descending manifold for Q is completely disjoint from the ascending manifold for P. And then I claim there exists f sub t, which lowers f of q to log of p. And when I say that, I mean, of course, that it doesn't do anything else, right? That's all it does. And this is sort of easier, than maybe that would have been a better warm-up to this problem. And maybe it's worth saying that the homotopy occurs and f sub t, best way to say it, is supported in the neighborhood of the descending q. And there's a similar statement if you want instead to raise p, you just do something that raises p and will support it in the neighborhood. Supported in the neighborhood means that it's constant in t. It doesn't vary in t outside a small neighborhood of the descending manifold. And the point is just, so again, we have, now we have sort of a simpler picture. I have f sub p, and p. I have my ascending stuff and my descending stuff. But I only care about my ascending stuff, and that's this perhaps. And then I have a Q, and they're just disjoint. It's just nothing interesting happening. Maybe this is going to both index 1 surface, for example. So, well, the whole point is that I can extend because this descending because these ascending and descending manifolds are disjoint. The key thing that all I care about, since I'm talking about lowering, lowering Q, right? Yeah. Since AP, the only thing I really care about is that D sub Q, the key, so I need that. D sub Q is a, let me see, so this is all inside a coordinate. inside a fixed coordism, and so d sub q goes all the way down the bottom. D sub q is a closed disk with the boundary of d sub q contained in, this is all a big coordism x from n0 to n1, with just these two credit points, so it's contained in n0. So it's really, the whole point is it just doesn't run into P. If it ran into P, then you have something funny, right? You have like sort of a closed disk with a little arc taken out of it, or something, a little ray taken out of it. And so, and F and their coordinates on, so their coordinates, let's say Q has index K, so their coordinates x1 up to xk on this descending line from Q, such that F restricted to PQ is equal to just the sum of the minus sides of K of minus xi squared. Where that puts that at level 0, and then it goes down to some, and then whatever the radius is, that's the bottom. Okay, and then I want to argue once again that I can just extend this to I can take local coordinates, then just take what did I just say, and f near p, the same coordinates, is the standard local. Right. And all I want to do is I want to extend that standard local model, right? So I want to extend the coordinates. So I get extra coordinates xk plus 1 up to xn that are initially just, those are the ascending coordinates. They're initially just defined near q.
So is that near Q?
Near q. Yeah, p is just not even in the picture, right? That's all we're doing. We're just avoiding. And of course, this argument, I mean, I could put zillion with critical points in there. The whole point is just as long as I don't get any other critical points. Extend xk plus xn to a neighborhood of full descending manifold, such that still f, so that f restricted to this neighborhood is still equal to the sum of the minus xi squareds, equal 1 to k, plus the sum of the minus k plus 1 up to n xi squareds. And the only difference here is, so this neighborhood now is sort of the set of points, x1 up to xn, such that the sum of the xi, the sum x1 squared plus xk squared is some large radius, is r squared, right? That's some large, so that's the radius of this large disk, all the way down to r, but the sum of the xk plus 1 squareds plus xn squared is some small x1, right? So it's a small tubular neighborhood of this large disk. Okay. That's the only difference. And so I'm just saying that there's a way to take the standard local Morse coordinates here, which are just in a neighborhood of this point, and actually extend them to local Morse coordinates in the full neighborhood of this descending manifold. Okay? And so the picture kind of looks like, normally the picture looks like here's x1 up to here's x1 up to xk, that's some large radius, and here's xk plus 1 xn, that's some small radius, and we're working inside this neighborhood here. And this radius is r, and this radius is x1. Okay? But the function is still the same, so level sets still look like this. And all I want to do is modify it so that the value of the function at this point is less, right? And, well, you can sort of see it from, so one way to visualize it, right, is, one way to visualize what's going on is, I now have a neighborhood, here's my descending manifold for Q, here's my ascending manifold for Q, and I have this neighborhood where everything looks standard. Something like that, and I'm just going to run a string over this saddle, and but I'm going to keep the boundary of this. So I've got this trough going up and over. I'm going to keep the boundary of that trough tight, fixed, and I'm just going to run a string through here and pull tight, and that'll go down to something like this. So that'll go to something like this, but I still have the same. Maybe I should draw it a little more carefully to make it more convincing. Now, in the transverse direction, I have this very large ascending manifold, okay? But everything stays fixed on the boundary. You can also, I will not attempt to write, you can write down a formula, I'm not going to do it. It involves putting a bump function in here, using a bump function, okay? But I can also draw what happens to the level sets. The key thing is we're supposed to stay fixed on the boundary, right? But we don't want the cross to be in this level set, because that's like at 0. Say this, for example, is let's say we want this one to be, this is a particular level, so that's the level we want to get P down to, right? So we still have this, but now we've got, originally, here was our level set, here was our critical level set, now we want it to be here. So we just deform it. Happens. And what I'm trying to emphasize is kept everything fixed on the boundary of this neighborhood, and we just change the level sets like that. And there's no real issue here. And so this used to be what's. And that allows us to switch heights. Okay. Any questions? So we put those things together. It might be ready to escape. Just from a practical point of view, suppose that you, the first way I led into this was saying if you wanted to cancel 2 critical points, you might need to move other stuff out of the way, right? Move it below or above before you cancel. Another good example where you might want to move critical points up or down is if you are preparing for a handle slide, okay? And if you want to do a handle slide, one thing I said is if you have, I was claiming that my description of the 1-parameter family that realizes a handle slide also gives you proof that if you do a handle slide, you produce the same manifold. There's one thing that's a little fishy about that is what if you were saying, let's do a handle slide, but the critical point corresponding to the thing that was supposed to be slid over was higher than the critical point corresponding to the thing that wanted to do the slide. Okay? So if you want to slide something up above, if you want to slide something low over something high, it has to get above before it can slide over, right? Before you can do this critical point has to get higher. And so, but that's also easy to deal with because if they're the same index, the descending and ascending manifolds are disjoint, and so then you can just lower this one, slide, and then bring it back up. And so sometimes, I'll just say that, sometimes you need to raise or lower critical point. Raise or lower critical point. To realize handle slides. fact, maybe I'll kind of try to give an example of that, and also let's see, try to do it in 5 minutes. Let's see. So the question now, here's what I'll do. I'll try to just to finish this discussion of cancellation of points. So let's see. Do we have the following statement? So the conclusion we'd like to have is that if the index of Q, if I'm given some random Morse function f from x to 0, 1, with lots of critical points, and two particular critical points, P and Q, which look like they should cancel. So what I mean by that is, this means, what I mean by that is that the index are separated by 1, so index of P equals K, index of Q equals K plus 1, and that there's a single flow line from one to the other. And there's this unique flow line of Q and P. I want to argue that then you can cancel. So the problem is that there's lots of critical points. So can we see that using this technique we can get all the other critical points out of the way? And so so how to get other critical points out of the way? The most, this is in general possibly overkill, but the most efficient thing is to, step 1, make the critical values ordered by index. What I mean is that f of critical point A is less than f of B implies index of A less than equal to index of B. I have 2 critical points. So in other words, you never have anything of higher index below something of lower index. Now why can you do this? Well, what we know is that anytime you have anytime you have something of higher index below something of lower index, we discovered that generically you should not expect the ascending and descending manifold to intersect at all. Okay, so that was something we figured out quite a while ago. So then that means that immediately you can switch their value. So you can always bring higher index things above lower index things freely. Once you have that, then you know that there's going to be these 2 critical points are separated by index 1. And they might, of course, there still might be lots of other critical points between them, but those critical points will be either index k or k plus 1. So what you'll have is you'll have sort of, you'll have Q and you'll have P, and then you'll have a whole bunch of other index k critical points and a whole bunch of other index k plus 1 critical points. But again, this is also index k, and this is index k plus 1. And so you can rise, so index k and index k critical points, you can also freely switch their order, because the ascending, this is the other thing we figured out, is that if their indices are the same, you expect their ascending and descending manifolds to be disjoint. So if you expect, when the indices are the same, we did a dimension count, you don't expect any intersections. So you can just lower these, right? So bring all those down and raise those, bring all those up, and you get to the point where there's nothing in between P and Q. And when there's nothing in between P and Q, and here's all this other stuff, here's all this other stuff, and now you can cancel. Okay? This fact that along the way, we use this making the critical values ordered by index, and that's just a useful thing to do anyway, right? If you want to organize your animal decomposition or anything else. I'm going to stop now. We're almost ready to start trying to prove. I think the first thing I want to prove is that every three manifold bounds a four manifold. I actually don't need most of this, but I want to work towards proving Kirby's theorem on surgery, how to relate two different surgery diagrams of a three manifold Kirby calculus. And we're sort of almost have all the tools we need.